Hi, I'm meteorologist Matt Sanders. This is a sailing weather educast brought to you by Sailing Weather Service and U.S. Sailing. In this educast, we are going to take a look at the winds and strategy around updraft clouds. But as always, remember this is a lesson, not a forecast, so make sure you check the actual National Weather Service forecast before you set sail. So in this educast, we're going to look at how the wind caused by an updraft cloud interacts with the large-scale wind to cause the observed wind that we sail in. Essentially, the wind from the updraft cloud plus the large-scale wind is going to equal the observed wind we sail in. This will play into some strategy you can use when sailing near updraft clouds. But to do this, you're going to have to rely on your cloud identification abilities that we learned in previous educasts, specifically being able to identify updraft clouds as low-level cumulus that are not precipitating, as discussed in the low-level cumulus educast. But just as a quick reminder, here's an example of an updraft cloud, and you can visually see it's not raining below the cloud, and there is air rising into the cloud potentially from near the surface. So let's imagine that cloud over a race course. So here we're looking down at the top of the cloud that is in the center of a race course, and ideally the wind is going to be coming equally from all directions around the cloud to supplement the air that is rising into the cloud from below. And for the purposes of this example, let's just assign a value of 5 knots to the wind caused by the cloud. Now, this cloud-induced wind would be the wind we sail in if there was no large-scale wind caused by features such as high and low pressure centers, but we know that's not the case. So we need to remember that there's always a large-scale wind, what you may have heard referred to as the gradient wind. And in this example, our cloud is going to exist in a 10-knot gradient wind. So in this location of the race course, to recap, we have the wind caused by the updraft cloud at 5 knots and the gradient wind at 10 knots. And some combination of these two winds is going to result in the observed wind that we actually sail in. Now we can easily figure out this observed wind by doing some simple addition and subtraction around the cloud. So remember, in this location there was a 10-knot gradient wind and a 5-knot wind caused by the updraft cloud. Winds are traveling in the same direction in this location, so they add up to the observed wind, which is, in this case, 15 knots. Now on the other side of the cloud, we also had a 10-knot gradient wind and a 5-knot wind caused by the updraft cloud, but they're flowing in different directions. So in this location of the cloud, the winds partially cancel each other out to cause a 5-knot wind. And this occurs to a varying degree all around the cloud based on the direction and strength of the two winds. So if we reapply the race course, you can see how this can play into some strategy. Looking upwind, you can see that the winds on the right side of the course are veered, or what some call right shifted, while the winds on the left side of the course are backed, or left shifted. There's also some impact on speed. If we look upwind at the cloud, the wind at the front of the cloud is decelerated and lighter, and the wind near the back of the cloud is accelerated and stronger. So talking strategy, if you take the right side of the course on port tack as you leave the starting line, you'll initially become headed by lighter winds. And then when you tack on to starboard, you'll initially become lifted by stronger winds, but then progressively headed as you sail towards the rear of the cloud and the top mark. However, if you have more of an option of where you can sail around the cloud, you may want to avoid the front side of the cloud in what we're going to call the no-go zone, because this is where the lightest wind in relationship to the cloud is going to occur.